So welcome to today's session. This is session 8 on phase transformation materials. So in previous sessions, we have discussed different types of nucleation rates and nucleation types, and also we have done for different shapes. We have to try to derive different nucleation rates, and also uh, we try to like even discuss the different types of phase transformations and also bits and pieces of electric reactions, right? Where involvement of solid and liquid phase transformations. Now, what we're going to do, we are going to try to deal with the solid-solid phase transformations, which are mostly dominated by the diffusion transformation, where the diffusion of atoms defines the what type of phase is forming. So, without any further ado, let's start. So, in this one, we can see different types of transformations, right? So, yeah. So, these three, what does these three represent? These three represents a type of phase transformation or called as a precipitation type. So the A represents precipitation. Precipitation. It's nothing but if suppose if I have a solid and with decrease in temperature, the solubility limit of uh, B atoms will saturate, and then they will try to come out from the alpha phase. And what happens after that? So this alpha will transform into alpha plus beta. So this stage or this phase will remain the same even after the reaction, but some part of it will transform into a different types of phase with a different crystal structure of a different composition, right? So that is about precipitation reaction. Now moving forward to yeah, this will come under the eutectoid type, but in eutectoid you have one type of phase will turn out to two different types of layers, right? So that is what we discussed in eutectoid, but it resembles to the eutectoid in such a way that so one phase will transform into the same phase plus a different phase. So that is the precipitation uh, type reaction, right? Now, you can see here the first one is the famous one, the eutectic type. So this is eutectic. This is the eutectic type, and again, this also has this liquid. Suppose this is my liquid, then this is my alpha plus liquid, where alpha plus liquid is turning into my beta, right? Now, here again, the eutectic phase transformation, you can see alpha will turn out to be alpha plus beta, which is another phase, which is another type. So these all three types represent the precipitation type. Now, moving on to this one, which is B and C. Let's talk about only B. And what does B says? B says it is eutectoid, eutectoid type phase transformation. So it tells about the eutectoid type of phase transformation. Now, what about C? Now, these are phase transformations, right? So these are like diffusional phase transformations, diffusional type, where they require the diffusion of atoms. So that's why we call these all these type of reactions or transformations we call as a diffusional type phase transformation. Now, first one is precipitation type, which is according to eutectoid type phase transformation, right? So this is about this, and this one, well, alpha will turn into a alpha dash. This one is order disorder phase transformation. Order disorder phase transfer. Right. So what does it order disorder phase transfer type of phase transformation? So it means, let's suppose if I have A and B type atoms. Okay. Now let's draw a simple or big body center bar. Okay. Now, let's say this is my A atom and these are my B atom, right? So A atom is this one, B atom is this one, right? Now, what is a disordered state? Disordered state is nothing but the probability of occupying A atom and B atom is same. So that means it will draw in another one. It will be more suffice. Yeah. So this is my actual one. So let's say this is my ordered structure. Why this is my order structure? Because wherever you find in this type of material, let's say this is the AB structure. So wherever you find in this type of material, you see the crystal structure where B atom takes body center and all A atoms takes corner atoms, or B takes the corner atoms or A takes the body center. So the positions might change, but the distribution will not. Now, what about the disordered state? Now, again, let me draw the FCC, phase center cubic. So these are my atoms. And the probability will be half. That means there is a probability of A atoms occupying B sites or B atoms occupying A sites. So A can occupy. So let's say the probability of A occupying here is half and probability of B is occupying here half. What about here? If A occupies here, then A must occupy this position. So that's what it means. It's as a conditional probability. So if A position takes this place, then another A atom must take this place. What about here? If A atom takes place here, then the other A atom need not to take place this way. B atom can take place. So that is how the order disorder transition takes. Now, what is the next one? So again, same here. What about D? D is massive transformation. Now, what about D? These two are called massive transformations. Massive phase transformation. Right. So these guys are order disorder, and like the next one is the massive phase transformation. Now again, what is massive phase transformation? Here you can clearly see that. Let me draw the phase diagram here. Okay. Let's say yeah. So let's say this is my beta. Let's say this is my gamma. Okay. Now this is my alpha. Here is alpha plus beta. Right. Let's say this is also alpha. Okay. Now this beta it is transforming into the alpha. Okay. So what does that mean? What does that mean is, let's say this is my gamma, and draw it more clearly so people can understand. Now, why I'm drawing this one is because it is a metastable state. So when I'm trying to cool beta to very fastly, it will turn into the alpha, right? Without undergoing any alpha plus beta dissociation, it will directly turn into alpha, right? So that is what happens. That means when I'm changing my phase from one phase to another phase, suppose this is my alpha, suppose let's say this is my beta, is turning into alpha. They have different crystal structure. They have two different crystal structures. And so the beta is directly transforming into Directly transforming into alpha with same composition. See, there is no change in composition, just a straight line. Same composition. I hope it is understandable. That means when moving from beta to alpha, let's say this is my beta, here I am beta, and I suddenly drop to here to alpha. That means there is no change in composition, just the decrease in temperature. So there is no change in composition. The beta phase it's turning into alpha phase. So these next. The last one is yeah gamma to alpha, and these are only for pure ones, right? So pure elements, polymorphic. That means let's say iron at room temperature is BCC. It can be, or it is a alpha iron when heated about 914 degrees centigrade. Pure iron. I'm talking about pure Fe. Okay. This will turn into gamma FCC. The composition is same. It is pure iron, but when heating temperature, it changes its crystal structure from alpha BCC to the gamma BCC or the gamma FCC. Sorry. So from BCC to FCC, it changes crystal structure when heating from room temperature to 900 above 914 degrees centigrade. So that is known as polymorphism. Now, when I still heat it again, more than like what do you call? Let's say 1200 degrees centigrade, right? Or 1300 degrees centigrade, then this will turn out to be delta iron, which is again BCC in crystal structure. So when I heat it about 1536 or 1539, it will turn into liquid. So before turning into liquid, it undergoes three-phase transformations, right? Three types or three same type of phase transformation, which is the polymorphic phase transformation, where it just changes its crystal structure. Right? There is no change in composition. We are only talking about pure one. So that is about polymorphism. These are different types of phase transformations, which let's say this is my phase transformation, and it depends upon our temperature, right? And also the diffusion of atoms, right? And the diffusion again will depend upon the temperature and time, and also on different terms like what are the different types of crystal structure, and whether we are talking about what type of diffusion, and also we know the diffusion is of two types, right? There are two types of diffusion transformation, right? We have discussed there are two types of diffusion of atoms in a material. One is our substitutional diffusion, substitutional diffusion, and the other one is interstitial diffusion. Interstitial diffusion. So these are two types of diffusion we we have previously talked about, right? So substantial diffusion happens when the atom which is diffusing in a medium. Suppose substitution diffusion happens in, suppose if this is my crystal structure, or let's say this is my material, and my atom is trying to diffuse from here to here. Now the atom which is trying to diffuse in the material has same size of the whole lot, right? And interstitial diffusion happens when our the diffusing species is has a very small size when compared to the parent phase or the phase of the atoms in which it is diffusing. Right? For example, steel. If you take steel as an example, you have carbon as a diffusion species, and this carbon will diffuse in the iron matrix. And because the carbon atom is very much less in size when compared to the iron atom, so it takes the interstitials, interstitial sites. And what are those? They are called voids. And what are different types of voids? Octahedral voids and tetrahedral voids. So I'm not going to explain this again because I have already mentioned these things in previous sessions, right? So yeah, now and they, depending upon these, the diffusion happens and the phase transformation or phase change takes place, right? Now, yeah. So for any phase transformation to happen, we need two things. What are those? One is the nucleation of a new phase, nucleation of new phase in parent phase. Sorry. In parent phase. Yeah, nucleation of new phase in parent phase. Then growth of that phase or growth of the new phase. So these are the things in which the nucleation or the nucleation of growth defines how fast or how well how what is the extent of the phase transformation. Right? If growth rate is very slow, then all the only the nucleation of new phase will happen. Yet then you will have very fine structure. And if you have very less nucleation rate and you have very large amount of growth rates, then you have very coarse microstructure. Now, how do I say this? So, yeah. Now we know I have derived what is the nucleation critical nucleation energy required to form a critical radius, right? So I'm going to just write them again. So now, yeah. Before going to that, let's know what is the problem here. So this is my. I'm only concentrating on some part of some random phase diagram. Okay. So let's say this is my solidus line which separates two different phases. So here I have alpha, and here I have, suppose this is my thing, and this is my temperature plot, and this is my composition plot. This is the temperature and composition. So this is my equilibrium separation line of between two phases. Suppose this is my alpha, and let's say it is transforming into alpha plus beta, right? So let's talk about the precipitation one. So let's say what is the precipitation? Again, I will explain it again. So in precipitation, what happens is we are trying to reach a supersaturation state. Okay, now before going to supersaturation, let me come back, explain in simpler terms. Let's say I have composition x naught, and at x naught there are two phases, alpha plus beta. Right, this is my alpha extreme, and this extreme I have beta. So in between them I have alpha plus beta phase. Now, what if I try to reach a state where this is my T equilibrium 1, and this is my T equilibrium. Okay. Now what I'm trying to do is I'm trying to heat my sample to a temperature T1. So at T1, I have only alpha phase. That means everything that we have beta or any other phase will be dissolved into our alpha phase, right? So this is called as solutionizing, right? We have only one type of solution, right? There are no two different heterogeneous solutions. We have only have one homogeneous single solid solution phase, right? In that we have, yeah, so solute atoms dissolved in it. Now, after that, what I'm trying to do is I'm trying to quench it to the room temperature, right? So I'm trying to from T1 to quenching to T, the room temperature, right? So I'm quenching to room temperature. That means I'm retaining the high temperature phase to the room temperature, right? So that is what is called as quenching. So whatever the phase was up there during the high temperature, we are trying to quench it and reach to room temperature. That means we are thermal arresting or arresting the motion of atoms, right? So that is what it means. We quench it. That is, we are trying to retain the high temperature phase. And because room temperature has two different, because the room temperature has a different type of phase. So when what we're trying to do is we are trying to avoid the motion of atoms. So that is what we call as quenching. So at room temperature, the diffusion of atoms is very low. So there will be no formation of a different phase, right? So what we are trying to do is we are trying to form one type of a metastable phase, right, which is not a stable equilibrium phase. When we try enough amount of time, the atoms will diffuse and give a different type of structure, right? So that is what we are trying to do. We are forming a metastable phase, and this metastable phase has reached its what do you call solubility limit. What do I mean by that? So at T1, let's say at T1, I have complete solubility. At TE, I have again the complete solubility. When I try to move from below TE, like when I'm trying to cool slowly the sample, then at T2, I have my solubility limit of X1. And again at T3, I have solubility limit of X2. So X naught is greater than X1 is greater than X2 and so on. So that means with decreasing the temperature, my solubility limit or the amount of solubility of different B element in alpha phase is decreasing, right? So at room temperature, it should have X5, but while quenching, it has X0. That means it is supersaturated solid solution. It has more amount of solute than it is allowed, right? So that is what we call as a supersaturated solid solution. Now, so super saturated solid solution, right? So it has reached beyond the saturation limit of B atoms in alpha phase. Now what I'm trying to do? Now what I'm trying to do is, let's say this is my heating cycle. Okay, I took my sample to T1, then I tried to quench it at room temperature. So this is my room temperature. This is my T1. After that, what I'm trying to do is I'm again trying to heat it and keeping it there for certain amount of time. So this is my T2. So T1 is greater than T2, is greater than RT. Okay. Now this whole process again I will cool it down. Now this whole process is called as precipitation hardening, or people even it called as a age. Okay. So this is called as a age hardening is a little bit different. So let's call it as a precipitation hardening process where we quench it and then we again heat it to form precipitates. Now, while heating, we can control the shape of the precipitates that are being formed. Again, how? I will explain in a few minutes. So, this is our whole process why we do a precipitation. Right? We can control the size of the precipitates while doing this type of process. Why? Because while quenching, we have reached the saturation limit of B. So B atoms will try to come out, right? So that is obvious. So B atoms will try to come out. So that's how. Let's suppose this is my alpha phase. Okay. Now, because of the saturation, after heating, you will find precipitates. Right. So in alpha phase, you will find different types of phase. Beta phase. So you can control by doing this type of process. You can control the size of it. Right. So this is called as a precipitation reaction or the precipitation formation. Now, what are the different terms that it's going to depend? Let's draw for the homogeneous nucleation. So we know delta G total will be equals to minus volume times, let's say, the volume of a sphere. We are talking about a sphere of radius r. So my volume will turn out to be 4 by 3 pi r cube times delta GV, or the phase transformation or the change in free energy when alpha will turn into beta. So delta GV will be equals to G beta minus Gi plus surface area of the sphere times gamma SL, or S1 S2. Or you can write it as gamma alpha beta, right? Because beta is forming inside an alpha. And what is my area? Which is 4 pi r square. Now again, this is for if there is no strain or there is the perfect matching, right? We are talking about coherent precipitates, right? There is no mismatch. Now, if I try to find the critical radius, my critical radius will be r equals to r star will be equals to minus 2 gamma alpha beta upon delta G. So I have proved this many times in previous sessions, so I'm not going to prove it again here. I'm going to directly use that relation, right? So this is my r star equals to minus 2 gamma alpha delta G. And if I try to draw, um, and according to that, if I want to know the delta G barrier, if all I have to do is just substitute this by r 2 gamma alpha beta upon delta GV whole cube delta GV plus 4 5 2 gamma alpha beta upon delta GV square gamma alpha. From this we will obtain delta G star. Right. If I try to draw the total energy, then it will look like this. Delta GV is my R. So, and because we have a 4 pi R square relation, so it will go like this. So this is my area term. Now what about my volume term? Volume term will go like this. Now initially the area term will dominate, so that's why we'll have the summation will look like this. And this is my R star. For what? This R star 1. R star 1 is for homogeneous nucleation. Right. Now, what about homogeneous nucleation and also coherent precipitates? Now, what will happen? What will happen to our R2 star if again we have same type of nucleation but we have strain energy? What will happen if we have a strain energy? Right? So the relation will look like this. Delta G total will be equals to minus V delta GV minus delta GS. Some of that energy is going to accommodate for the strain at the interface. Right. So that is why we are removing some of the energy from the delta G beta. And again, as usual, you will have surface field. Right. For this one, again, everything will turn out to be delta GT will be equals to minus 4 by 3 by R cube. Right. 4 by 3 by R cube times delta GV minus delta GS plus 4 by R square gamma alpha beta. Now, for again critical radius, doing the same, differentiating with respect to R and turning it to be 0. So it will be 4 pi R square delta GV minus delta GS plus 8 pi R gamma alpha beta, which is equals to 0. Right. Now, when I try to equate it to 0, this R will be equals to, or if I take R as a common, that's if I take R as a common, then that will be 8 pi gamma alpha beta minus 4 pi R delta GV upon delta Ks equals to 0. Now, R can be equal to 0. One is R equals to 0. Then also, this term should be equals to 0. Let's say if AB equals to 0, then that means A equals to 0, either A equals to 0 or B equals to 0, or both can be equals to 0, right? So first of all, the R can be equals to 0. Now let's say if we equate this as also on 0, then let's take pi common, 4 times 1, 4 times 2, then this will be equals to R equals to 2 gamma alpha beta upon delta GV upon delta GS. So our R star has changed, and whether it increased or decreased, it increased, right? Because this term is decreasing, then this term will increase. So R2 star is greater than R1 star. Then that means the delta G star will also increase because it depends on R, right? So how does this diagram will look like? Let's draw this again. Delta GV, and this is my R star. Let's say this is my R square term. This is my R cube term, or delta GV term. This is for R1. Remove those things. This is for R1. Now what about for R2? So for how R2 will look like. For R2, again, this will coincide R2 and R1 for area. They are same. But what about here? Because this is for delta GV, and this one will have lesser negative values. That means this is delta GV minus delta GS, the strain energy accommodation. And because of that, so our R star or R1 star. Now what about for R2 star? R2 star, the barrier will increase. Why it will increase? The barrier will increase. Why it will increase? Because of the strain energy accommodation. This term has gone up. That means this term still dominates to an extent. Right? So that's why this value got increased. Right? So because of this strain energy, there is an increase in the total barrier. Now, so that is this gap, the delta GV minus delta G. Actually, it should this line should follow like this, but now because of the change, this is the line it should follow. Right? Now coming to that, how the nucleation and growth rate defines our crystal structure or the microstructure of the crystal structure, the size of the grains. Right? Now, let's take the homogeneous case, homogeneous nucleation, homogeneous nucleation case. Okay, let's take the homogeneous nucleation case. Now we have defined our R star as what? R2 star. Let's take the strain energy. Let's not talk about the strain energy. Okay, even we can include the strain energy in this term, but for simplicity, let's remove the strain energy part because it's simple. The only term is you have to remove some part of delta GB. That means if you are adding a strain energy, right? So yeah, so R2 star will be for simply R star will be my 2 gamma alpha beta upon delta GB. And why I'm putting modulus terms here? Because delta G is a negative value and R radius is a physical quantity which cannot be a negative value, right? Because you physically measure it. So you cannot physically measure a negative value, right? So nobody says minus 2 meters. So it just, if someone tries to ask you measure what is the length of this, we say 1 meter or 1.5 meter or 1 centimeter or 10 centimeters. We do not say minus 1 centimeter, right? So that's why we are putting a modulus term here. Right? Or you can write it like this also. You can put minus beforehand such that this whatever the delta G value will take care of that. Inverter will take care. Right. So that is the reason why we keep negative value here. Now coming back to it. So yeah, I have defined this curve also. This is R square, this is R cube. This is my will not look like that. Yeah, so this is my delta G star, the amount of energy, right? Now, so the number of nucleation sites will be equal to frequency times what is the number of nucleation sites. And because we are talking about homogeneous nucleation, every site has an equal probability to form a nucleation, right? So that's why we put test C naught times the frequency with which the stable nuclei will form times or exponential time. There is a probability of forming the nuclei, right? So let's say it is in molar value. So let's take as an RT. instead of kT, because we are mentioning this is mole per joule per mole per Kelvin, right? So that's why I'm mentioning delta G star. Now, this is for the nucleation sites, how the number of nucleation sites are forming, right? And this all will turn out to be exponential if I try to substitute this delta G star. After substituting this R star and delta G equation, I will get the delta G star. And if I substitute the term will be, then what happens? So if I have a larger undercooling, let's say it is exponential 1 by function of delta t. And we know delta G is a function of delta t, right? So delta GV will be equals to delta H times delta T upon T equilibrium. So higher is the undercooling, the higher will be the delta GV value. Right. So it finally boils down. So this is the term, and if I substitute all those terms here, then the number of nucleation sites will increase if I try to increase the undercooling. Then that means if I try to increase the number of nucleation sites, then this term should also increase. Right. Now, when it will increase? It will increase if this term decreases, and this term will decrease if it has equation like this, right? So if I increase the undercooling, this term will decrease, then this whole term will increase, and the number of nucleation site will increase. If you want, I can derive this one. The delta G star will be equals to, what was that? Yeah, minus 4 by 3 pi R star. It will be 2 alpha beta upon delta GV. There is also a 1 GV, so it is whole square plus 8, just 8, 4, yeah, 8 pi, it is 2 square 4, 4 to the 8, 4 4 square, 16, right? It should be 16. Because you already have 4, another 4 will join you, so 4 times 16, and this will be gamma alpha cube upon delta G V square. Now, so how much will this one? This one is at 24. 24, it will be 32, right? So 16 times. So let me draw it again. Yeah. So here I have 4 pi r square. Four pi r square will be 4 gamma alpha beta upon delta GV square. This will turn out to be cube. So it will be 16 pi. And when I do this, this will turn out to be 16. If I take 3 common, then there will be 16 pi gamma alpha beta whole cube upon 3. This 3 will be the delta GV whole square. Right. So yeah, this will be 16 times 3. 4, right? 48, 16, 48. So 48 minus 32 will be 16. So that is my delta G star. Now, N homogeneous will be equal to C naught, the frequency, times the exponential, no, uh, yeah, delta G star upon RT. Right. So what is my delta G star? Delta G star will be equals to 16 pi alpha beta cube upon delta GV whole square. And what is my delta GV whole square? Delta GV whole square will be equals to delta H square times delta T square upon TE square. So if I substitute there, then 16 pi gamma alpha beta whole cube times TE square upon delta H square times delta T square. And these all terms can be taken as a constant for small undercoolings or minimum undercoolings. So this will turn out to be A upon delta T whole square. Right. So this is my 1 by exponential, because there is a minus, A by delta T whole square. So if I increase my undercooling, this term will decrease and this whole term will increase. This term will also increase. So that is how I came to that relation. Okay. Now, what is my frequency? The frequency is nothing but what is the probability of the atom jumping. So once I reach a critical radius r star, what is the probability of an atom jumping from beta phase or the alpha phase to beta phase to grow that nucleus, right? So that F will be depending upon the random jump frequency times the coordination number, right? Times, so how many directions do I have? 6 times the probability of the successful jump probability. That will be delta G, let's say delta Gn, okay? For simplicity, let's just assume delta Gn upon RT. Again, let's all take all these terms constant, which is C1, then N homogeneous will be equals to, please remember, C naught is nothing but the initial concentration, right? C naught times C1, let's say this as C2, and that will be equals to exponential minus delta Gm upon RT times exponential delta G star upon RT. Now, if we decrease the temperature, that means we are increasing undercooling, so this term will increase. This term will increase. But what about this term? This term purely depends upon temperature, right? So that means if we decrease the temperature, this term will also decrease. It is straightforward, right? Because if you decrease the temperature, then the temperature decreases. That means the average kinetic energy of the atoms decrease. The number of jumps will also decrease. So atoms will be more sluggish to diffuse. So there are two opposing terms here. One, if I decrease the temperature, the undercooling increases, the number of nucleation or the nucleation rate and homogeneous will increase, the actual nucleation rate will increase, but the diffusion of atoms will decrease. That means if I try to do fast undercooling, that means the fast cooling, then I have more number of nucleation sites formation. But do they grow? The growth depends upon the diffusion of atoms. So they won't grow much. That means you have, after reaching room temperature, we have very fine grain crystal structure. Right. So it's not very well. So remove this part. Yeah. You will have very fine grains. Now, if my undercooling is very low, right? So if my undercooling is very small, if my undercooling is very small, then there is my nucleation barrier. This will decrease. That means the nucleation rate, which is the C, will decrease. But the diffusion of atoms is very high because we are very close to the liquid temperature, right? So the atoms is still they have very high amount of kinetic energy and they can easily jump from one atomic site to another atomic site. So that means we have very small, very low number of nucleation sites when compared to the previous one. But we have huge amount of, I mean, large amount of diffusion. The grains will be larger, right? So the grains will be very much larger when compared to the high nucleation rate one. So this is how we control the microstructure. No, the microstructure. Yeah, the microstructure of any material while heating and cooling. Heating and cooling. Now the same goes for the precipitation. So let's say, and we know we have taken an example of alpha and beta. So that means beta is rich in B. This is rich in A. So if a precipitate forms, let's say this is my beta precipitate and this is my alpha region, right? So this is my alpha region, this is my beta precipitate. Now, if my precipitate wants to move, right? If suppose, just like I have said before, so this, let's say I have defined a certain amount of undercooling and also certain temperature where the diffusion also takes place and also nucleation also takes place. Now let's focus on diffusion. Right? Let's suppose my precipitate has formed. I've done my transformation. My precipitate has formed. Now, if it tries to grow, what will happen? Let's suppose this is the front velocity. Front velocity, it is moving with v as velocity. That is given as dx upon dt, which is the rate of change of displacement or rate of change of distance upon time, or rate of change of distance with respect to time. That is velocity. We all know that. Now, how do we relate this one to our diffusion? We know diffusion will be equals to the diffusion of atoms, right? And because the precipitates need more amount of B atoms, so the B atoms will come from here to here, right? So that is how the diffusion takes place. Because of the concentration gradient, C naught CE, you have diffusion happening. And that is given by minus D, the diffusion of B atoms in A times dou C upon dou X. Diffusion atoms of B in A. Now what is this will be equals to, what is the velocity front? V times the concentration. And what is the concentration difference? C beta minus C naught, which is equals to minus dBA dou C upon dou X. Our velocity will be equals to D upon C beta minus C naught, or if I take dC upon dx. If I take concentration only depends upon X. It's the exact differential, not partial differential. If it doesn't, if it, let's say it doesn't depends upon time, right? You have also a steady state diffusion. Now we need another equation, right? Because how do we write this dc by dx, right? So to do that, whatever the species, there is a conservation of mass. Whatever the species that have been diffused here are being eaten up by beta precipitate, right? It is taking more and more amount of B atoms from alpha phase. So that is what's happening here. So what is that amount is given by this simple area one. So this area will be equals to C beta. Let's say the thickness of precipitate is X. C beta minus C naught times X will be equals to half into, let's say this is an right angle triangle. So half into base into height, right? Half times what is my base? L times what is my height? Delta C naught. Which is C naught minus C. Right? If I write it for like more simpler form, then this will be equals to V equals to D upon C beta minus C equilibrium times what is my DC. Let's take the change, the maximum change. There is no minimum change. Delta C naught upon what is my L? This is my L, right? So this is L. Now we know what is L here. From here, L will be equals to C beta minus C naught upon X divided by delta C naught times 2. Now if I substitute this here, V will be equals to D upon C beta minus CE times this will become delta C naught whole square. This 2 will come here and C beta minus C naught times X. So this is my velocity front with which my precipitate will grow, right? Now that is what I'm trying to show here. And suppose if undercooling is high, see this will if undercooling is high, this will increase with respect to the undercooling, and if the temperature is increased, this also will increase, and there will be a critical point where these two are optimal. For example, if I am talking about at this temperature, then this one is high, this guy is high, but this guy is low. The diffusion is low, the nucleation rate is high. And if I take the temperature here, the nucleation rate is high, the diffusion is low. So every point there is a critical point where both these two have optimum values, right? So this is called as a critical temperature where the nucleation rate and the diffusion are maximum or optimum. I shouldn't say maximum. Right. Now, we have studied the diffusion mechanism of how the precipitates grow and how the undercooling and temperature affects the nucleation rates and our diffusion of atoms to form precipitate. Right. And also, the velocity front will increase if there is a concentration gradient between the beta precipitate and alpha. So that is very important to remember. What is my delta C naught? Delta C naught is directly proportional to the concentration difference between the C alpha and the CE, right? So that is what I want to show. If there is a higher, more amount of concentration gradient, more will be the formation, right? The velocity front will increase. Now, I'm not going to prove these TTT diagrams. These are called TTT diagrams: time, temperature, transformation diagrams. In short, We call them as TTT diagrams. There are also CCT diagrams, which are called as continuous cooling transformation diagram. So if we have enough time, or I don't know, sir might or may not discuss, but if you have enough time, I can teach this in the extra session. I can derive these things in extra sessions. Okay. For now, I'm going to only explain. So how, what are the different things that have been given here, and how we use them to know what is happening, or what type of phase, what are the combination of phases that can be formed with respect to the cooling one. Okay. Now let's first see the B1. So F is my fraction transform, fraction of, yeah, phase transform. So F is my fraction of phase transform. What do I mean? That means let's talk about any phase transformation. Okay, let's say eutectic phase transformation. Alpha is turning into alpha plus beta. This forms a phase, like eutectic one, like let's say laminar phase. Okay. Now, fraction tells me how much of alpha is being transformed into alpha plus beta. So that is what my F, or the fraction of phase transform, defines. Fraction of phase defines the how much of phase is transformed from alpha to alpha plus beta. That is F. And my y-axis is time. The how much time it is taking to totally transform, or to transform alpha to alpha plus beta. So F has values from 0 to 1. 0.1 means 10%, 0.2 means 20%, 3, 30, vice versa. 1 means 100% total transformation. So log T, and because the time can be varied. For example, if I'm talking about low nucleation rate and high growth rate, so it takes large amount of time because the grains needs to grow and cover the whole specimen, right? The whole need to transform, cover the whole face for alpha phase, right? So that is what here. Now, at higher temperatures, or let's say if we have a large amount of undercooling, so this is T1, T2. Let's define T2 is less than T1. T2 means TE minus T2, or TM, or T transformation start temperature is less than Tm minus T1. Right? T2 is very far from Tm, and T1 is very close to Tm. Right? So there the difference will be, sorry, larger, right? The difference is larger. So that means undercooling is more here than here. That is what it means. So undercooling is more at T2 temperature than T1 temperature. That means the nucleation rate is high here. Here nucleation rate is homo, homo, low here. So it takes this much amount of time for high nucleation rates. And here it takes long duration of time. Why? Because of less undercooling. That means less amount of nuclei formed, and these nuclei have to grow, and that take enormous amount of times. So this is my start at T1, this is my start, and this is my finish. And if I try to draw with respect to the temperature T2, so this is my T2, and this is my point 1, point 2. And for T1, it is my starting one, this is my starting one, and this is my ending time. So this is my start and this is my finish. So if I try to draw this at different, so if I try to draw these curves, these points for different temperatures, then these will look like at different temperatures. This will look like two C curves, right? So this is my start one, and this is my end one, and in between you can have 50%, 20%, 10%. If I try to, let's say for 10%, this is my starting, so this point will come here. Here's my 20%, this will come here. 30 is 50 here. So that is how we draw this CCC, TTT diagram. Now CCT diagrams, nothing but we introduce a cooling curve, and wherever this line touches, that is how our microstructure is. That means if it touches here, that means there is a start, and if I reach here, that means the 50% is transformed, and if I reach here, the 100% is transformed. That's all. So that is how it is used, CCT curves and TTT curves, to know the microstructure. Right now, let's talk about most famous precipitation one, which is the copper aluminum one. And the final precipitate we form is CuAl2, right? Yeah. Finally, we form CuAl2. Okay. Now, how do this precipitation happens? Now, once the final precipitate forms here, so once the precipitate forms, it is our beta phase. It has totally incoherent structure. That means there is no matching between our alpha phase and our precipitate. That means there is a large amount of, this is my delta G, that will be equals to minus V delta GV plus A gamma alpha CUI. And because it is totally incoherent, this this whole term will be very much higher value when compared to this. So there is very little amount of very low amount of delta G, or the free energy that is available to transform alpha phase to the theta, or we call it as a theta phase. Theta, it's called as theta, which is totally incoherent, which takes large amount of interfacial energy. And because of this, we will have very low or very small amount of free energy change, the total free energy. Now, how do systems like this tackle this type of problems? So what they do is they first form a different phase, which is the GP zones or granular crystal zones. Now, what do they mean? The granular crystal zones mean that it is a type of phase where it is totally coherent with the surfaces. It is totally coherent with alpha phase. What is my alpha phase? This is my alpha phase, which is cubic structure, right? Because all three sides are have, first of all, it is a cubic structure, and why? Because all three sides are equal. It is 4.04 angstroms, right? So after that, and first it will form GP zones or the granular crystal zones. And how do they look like? They look the more or less they look like 2 to 3 atomic layers of aluminum, or 2 to 3 atomic layers of copper introduced in aluminum. Right. Suppose this is my aluminum layers, aluminum atomic planes. Then you will have 2 copper atoms coming in between them, or 1 or 2. One right here, for example, one copper layer coming in between. So there is total coherency on there. Now, after that, so first naught, alpha naught will turn into alpha 1 of a different composition and GP zones. Right. Again, if we give enough amount of time, these GP zones will convert into, will give out their atoms, and again there is a formation of theta double prime. Now, what is theta double prime? Theta double prime, they form spherical like structures, and here you have plate like structures. Like again, you can see the all sides are coherent. Next, after that, you will have alpha 3. Why? Because more and more amount of B atoms are being rejected. So this will turn into alpha 3 plus theta prime. Now, theta prime have two incoherent sides, one coherent or semi-coherent side. Next, it will turn into alpha 4 of theta. So, and transforming from one point to another point, let's say it transforms from alpha naught to alpha 1 plus GP zones. So, the energy rise will be much smaller. So, this is my actual energy rise. So, during transformation from alpha naught to alpha naught to alpha and GP zones, this is my total rise. Right. So, system tries to attain that phase with a minimum increment in the behavior. Right, for this one, this is my one, and for the second transformation from GP zones to alpha to theta to double prime, again it will have similar amount of this. So finally they add up to this one, the final one. Right, so that is how the system will accommodate the totally incoherent precipitate. Right. Now, this is my free energy versus GP zones. Now the free energy versus the composition diagram at a given temperature. Right. At temperature T1. What is happening? So at first, I have GP zones, which are rich in copper. Right. So this is my X of GP zone, composition of GP. After a certain amount of time, these GP zones will dissolve, and there is a formation of theta double prime. And theta double prime will has composition of this one. After some amount of time, again, the atom will be rejected into the alpha phase, and alpha phase will become richer. So alpha 1 composition alpha 2 is composition alpha 3 composition of theta prime composition theta. So composition of alpha 4. So what does they tell you? They tell us that composition of alpha 4 is less than composition of alpha 3, less than composition of alpha 2, composition of 1. That means this one has a higher composition, higher composition, this one has a lower composition. Right? Now, so the total energy is decreasing from here to here. Right? And because of this decrease in energy, these type of reactions are possible. Right now, so for GP zones, the alpha 1 composition is in equilibrium with mole fraction of GPG, the composition of GPG. Right? This is the equilibrium composition at equilibrium. Now, for theta double prime, x alpha 2 is in equilibrium with theta double prime. Right? And based like this, based upon this, the x alpha 4 is in equilibrium with theta x theta or x theta double prime, the composition of the theta. Right. So with time, this is how the reaction takes place. Now, moving on to the next one. So this one I have already mentioned before that at first I have a GP zone. At first I have an alpha naught. Then this will dissociate. This alpha naught will dissociate into alpha 1 plus GP zone. GP is nothing but granular crystal zones, which are nothing but the few layers that are being accommodated or introduced in our alpha naught. Right. Now, yeah, please. Yeah. Alpha naught, alpha 1 plus GP zones, and this again, this alpha 1 plus GP zones will turn into alpha 2 plus theta double prime. They again will turn into alpha 3 plus theta prime. Finally, alpha 4 plus theta. And based on this is how my energy barrier will take place. Right. So total free energy will not drop directly from here to here, and because system needs to accommodate large amount of energy, so what system tries to do is system tries to uh, minimize the sudden drop, and it happens slowly. It happens a step by step. Right. At first we have alpha naught, you will have formation of GP zones, theta double prime, theta prime, finally theta. So that is how my total energy is being minimized. Right, how the total interfacial energy is being accommodated. Right, so this is about the phase transformation or the different types of phase transformation during precipitation hardening. Now, how do we control what type of precipitates or how which type of precipitate to be formed? Okay. Now, and also there is an important one, like we will come to this in a later in a few minutes. Yeah. How first one is how to control which type of precipitate to be formed. Now, the next question arises is why we are going to form these precipitates? Why we are having, why go through so much trouble to form this type of precipitates? Right. The answer is to increase the mechanical properties. To increase the mechanical properties. So how we are going to increase the mechanical properties, right? So let's say alpha phase is FCC. That means we know there are slip systems So deformation is nothing but moment of dislocation, and for the dislocation to move, there needs to be some slip. So dislocation nothing but moment of slip, moment of planes, right? So dislocation motion results in deformation, and dislocation motion is nothing but movement of planes on top of another. So we need to have a slip. So these are slips, the moment of planes, so one plane to another. That means one plane is slipping on another, and we need to have a successful slip. We need to have a good slip systems, right? So FCC has its own slip systems for dislocation to move. Now, has its own slip systems. So dislocation move in the slip system. For example, for FCC, the dislocation motion will be along the closed pack plane. Now the closed pack plane will be 111, and the direction is 110. Right. So for FCC, this is my slip plane. If this is my slip plane, where is my slip plane? Which is 111 plane. And my slip direction is along this. Let's take this as 110. So the plane must be, let's take 1 bar 1 1. Okay. So let's say my slip system will be 1 bar 1 1 1 bar 0. This is my slip system. Right, because the planes are represented in this and directions are represented like this. Right. Now, and for dislocations to move, there should be no obstacle coming, and one of the obstacles are the grain boundaries. Why the grain boundaries? Because at grain boundaries, the orientation of planes is different, right? So dislocations are moving in this direction, and they suddenly have to change their motion. So because of that, this grain boundary is an obstruction for dislocation motion. One is that, and the next one is the precipitates. Why precipitates? Precipitates have a different crystal structure when compared to our alpha phase. This is my alpha phase, and this is my precipitate. This is a beta phase. Now, because of this coherency strain, we have strain here. Okay, this is fine. There is my spherical precipitate, and it has its own strain around it because of the atomic lattice mismatch, right? And dislocation itself also has its own strain around it, right? When these two strains when these two strands come near each other, because of this strain, these two strands accommodation, the dislocation motion will be obstructed, right? So one is our grain boundary where the dislocation motion is being obstructed, and the next one is a precipitate strain field. The precipitate forms its own strain field, and because of the strain field, the dislocation cannot move further away, right? When it's being stopped, right? Now that's why we form precipitate. Now, if the precipitate is small, then okay, the dislocation will try to move, or if it cannot move, then it will try to cut the precipitate. So that means it requires more amount of energy. It requires the more amount of energy to move the dislocation through the precipitate. Right? It will more or less the precipitate will look like this because the top of the precipitate will be moved with respect to bottom one, and that's why it looks like it was being cut. Right? So yeah, this is one type. This is one way for dislocation to move law, to move the obstacle, right? And what if the precipitate size is too large and the dislocation cannot cut it? Then what does it do? It will just loop around. Let's say the dislocation is coming here. Now, after some time, if it knows that it cannot cut the precipitate and the precipitate is large, then the dislocation will do a loop around. And finally, there will be a dislocation loop, and the dislocation will fully over. And this mechanism, this whole mechanism is called as a OR1 mechanism, where the dislocation will loop around, move around our precipitate, right? This is my precipitate. And the beta, the dislocation will move from here to here. Now, so how do we maintain that shape and size such that our dislocation have to cut through? So that means we need to apply, and also this also will depends upon how the precipitates are distributed. For example, what is the distribution of precipitate? And this is my distribution, and this is my one type of distribution. This is distribution one. This is my distribution two. For let's draw this one. Yeah, for same length, right? For suppose the distance here to here is same. Let's assume it is same. If the precipitates are very closely formed, like the distance between precipitate is very less, then the dislocation has to form many loops, right? What about here? It only need to form one loop, two loops. First it comes here after time t2, and after time t3. So again, the distance between the precipitates will also define this how much strength, how much strength is required, or how much energy is required to move the dislocation from one point to another point, from one to two. So again, the distribution of precipitates will also define our mechanical properties or the yield strength, right? Now, yeah. Now, how coming to that question? What happens if we have if the alpha is very rich in B? So this is how that is what we are showing here. This curve we did different aging times, we did different precipitation hardening for different samples of same copper aluminum alloy, but of different composition. So one is 2%, 3%, 4 and 4.5%. Yeah, and also at different temperatures. This is for 130 and this for 190. Let's talk about first at low temperature. At low temperature, what happens if composition of copper is changed? However, yield strength is changed. Right? However, composition, for example, we change the composition of a copper, however, yield strength will be changed. Let's talk about low temperature. Now, as I have mentioned before, the velocity of that front will directly depend upon the concentration gradient. Right? If you can recall here, see, yeah, this one, the delta C naught, which means the composition of alpha minus the equilibrium composition of beta and alpha phase, right? More is this gap, the higher is this gap, the higher will be the front velocity, right? That means the 4.5 copper weight percent will form GP zones very fastly, right? So that is my aging time. At minimum amount of time, we can form our GP zones. So after GP zones, our yield strength will increase because of theta, because GP zones have coherency. And when you move on from the GP zones to theta prime, there is still coherency, but there is strain, and because of the strain, uh, there is no accommodation for dislocation motion. That there is a dislocation needs more amount of energy to move. So that's why the hardness is increasing. The yield strength is increasing, and again, and once you form theta dash, again this will increase to theta now again, because the composition of GP zones is very higher, the number of GP zones is low. Now, when you're going from GP zones to theta prime, because of the composition is getting decreased, the number of precipitates will also increase. And right, because of that increase in precipitate, there is increase in yield strength. And there is a combination of where we have combination of theta and theta double prime. And because theta double prime doesn't have coherency, there is the Oron mechanism. We need our dislocation to cut off the split. That means more amount of energy is needed to cut the split when compared to the Oron mechanism. So when we are going from theta double prime to theta prime and theta, so there is more and more amount of Oron mechanism formation, more and more cutting off the splits. That means less and less energy is required. The dislocation can easily move. That's why you can see the drop here again. The drop of yield strength. So we need to have a good number of theta precipitates and also theta double prime. So that is where the combination of theta and theta double prime will come here. That gives our maximum yield strength. Right. Now, if a composition of copper alpha is decreased, where there is no formation of it requires larger and larger amount of time to form GP zones and theta double prime, theta prime, theta double prime. Right. So that is about this one. Now, next, what about the temperature? Let's say the temperature is increased. Now, as I've said before, if the temperature is increased, the diffusion of atoms will also increase. Right? At higher temperatures, you can see there is no GP zones at all. Why? Why? Because coming to here, I'll explain this in a few minutes. Yeah. Because we have seen the TTT diagrams, right? So if I try to draw the TTT diagram of this guys, the precipitate ones. This is my final one. Check the 100% one, which tells me that there's a 100% transformation. And here there is a 100%. That means you will have theta plus alpha. This is my starting one, alpha naught. And at lower temperature regime, like below this nose part, you have first, let me draw with, let me erase this part and let me draw it more bigger one. Okay. Let's say, right now, the first one is At first, you have GP zones. Right, let me draw GP zones with blue. Okay. At first, you have GP zones at lower temperature. This is my GP zone. Okay. Now the next one is, if I try to increase my temperature, the next one is my theta prime. You can call it as a theta double prime. Right. After that, I have what? Theta prime. Pardon my drawing. So at first I have the GP zones, theta double prime, theta prime, and I finally have theta. Right. So what does that mean? What does these things mean? So let me extend my blue line. This is my blue line, GP zones. Then I have theta double prime. I will come here, and the green one will extend. Yeah. So let me erase this. This is how it actually looks. Then I have green one. Yeah. So this is my log T. Now let's say I'm at temperature T1, T2, T3, T4. So if I am at T1, I will first begin with G. So this is my continuous cooling curve, right? So let's say this is my continuous cooling curve. It is not even appearing. Let's change this color to violet one. So this one is starting here. I've started my cooling. So at first I have started very fast. So I did my quenching. Right, this is my quenching. Then what I did was, after some time, then I try to heat it, and I maintain it at this point. So I touch my GP zones. So my GP zones will start forming. Right, after a certain amount of time, everything will be converted into theta double prime. Let me mention these things here so that people can understand. So this is my theta prime, theta double prime, GP. Right. At first, I have touched my GP. Then, with time, this GP will be dissociated, and there is a formation of theta double prime. Then, with time, there is a formation of theta prime, and after finally, I arrive to theta. So that is what happening here. Now, if I try to heat it very fast to T2, and then I try to maintain there, my first one that is forming will be my theta double prime, not the GP zone. Why? Because I have totally shunned the GP zone area, and I have reached to theta double prime. And if I try to reach a point here exactly, then I have the combination of GP zones and theta prime, theta double prime, right? So that is how it is forming. At first, I have theta GP zones. With time, there will be formation of, again. If I reach to a temperature T2, directly reach to temperature T2, the formation will be my theta double prime. Then I will have theta prime, and you can see theta double prime, theta prime, finally theta. What if I directly reach to T3 and then I stay there for longer duration of times? I have first theta prime, then there will be formation of finally theta, right? And if I try to directly reach T4, there will be directly formation of theta, there will be 1%, and finally 2%, 10%, 20, 30, 40, 50, 60, 70, 80, 90. This is my 99% of formation. So that is how these TTT diagrams and this or the CCT diagrams are used to predict the phases that are being formed. Right, these are experimental ones. These are not the theoretical. These are the experimental ones where we heat it and transform. We give certain amount of time, we quench it, and then we see the microstructure and we calculate the how much of phase that's being transformed. So these are all the experimental pressures. So this is how the GP zones, the precipitation or the precipitation hardening takes place, and how the hardness will. These diagrams tells you how it is changing, right? The hardness is being changed. Now, how the theta and theta double prime are being formed. So this is my theta theta. Now, these are different types of precipitates. You can see in aluminum silver, you will have GP zones of spheres or spear shape. Then you have gamma prime platelets, and you finally have Ag2A. And in aluminum copper, you have GP zones first the discs, then you have theta prime again the discs, and theta double prime as the plates, then you'll find CuAl. And you can even find this in aluminum, copper, magnesium, where you have the peculiar one, the rods. First, there is a rod formation, then there will be leads and other things. And you can observe in copper beryllium also, and also in iron nitride. In the iron nitride, where these forms alpha discs to Fe4n, this forms very strong ferromagnets used in magnetic properties. Right. So these are the different types of precipitates that can be formed here. Now, the next one is the eutectoid transformation. Yeah. Now, how this eutectoid formation transformation happens in steels. Yeah, in steels you have we call them steels if there is a composition of less than 2 weight%. If the carbon is less than 2 weight%, we call them as steels. And depending upon the composition of carbon in between 0 to 2, we have different types of steels like low carbon steels, plain carbon steels, low carbon steels, very low carbon steels, medium carbon steels, high carbon steels, etc. And about 2% you have cast iron. We call them as a cast iron. Right. So yeah. So steels are less than 2 weight% carbon. Right. Then we call them steels. And we know a deutectoid. And I'm not going to draw the whole Fe3C diagram. I'm going to concentrate on deutectoid composition. So this is my alpha. This is my gamma FCC. This is my alpha FCC. You will have alpha plus gamma. Here we have gamma plus Fe3C, because at this extremity we have Fe3C. Cementite, which is orthorhombic crystal structure. Here we have FCC. Here we have BCC, body centered and face centered crystal structure. Now, at this point is called as a eutectoid point. The gamma is transformed into alpha plus FHPC. And there is a lamellar structure formation. Here you can see the lamellar structure. This dark one shows Fe3C, and the gray area shows alpha. So this is how the lathe structure is formation. Now, if I have if I have high amount of undercooling, then my grain boundaries are grain boundary regions will be saturated with the formation of this alpha plus Fe3C. Right, because of the grain boundaries are more familiarized for the nucleation of this alpha and Fe3C, right? Because any phase can be nucleated at grain boundary, because grain boundary has high energy when compared to free energy when compared to the grain, because at the grain there is no crystallinity, right? There is more disordered structure, so there is a high amount of energy there. So that's why the grain boundary is more favorable. when compared to the grain. So that's why when you have a high end of cooling, the grain boundary regions get saturated with nuclear sites. Now, how do we control these rates? So here we can see depending upon the cooling rate, right? The again I have mentioned before for the phase transformation, for the phase transformation, you need to have the proper diffusion of particles. Right, you need to have proper diffusion of particles. That's what this means. So if we do not, so at first, so you need to have the proper diffusion of atoms. And what do I mean? Proper diffusion means at first there is a proper diffusion of atoms. That means up to this temperature, you will have, let's say my composition is 0.8 weight%, which is the composition where here this is my 0.8 weight%. Okay, so gamma will transform into alpha plus Fe3C, right? So at 0.8 weight% carbon. So at T1, up to T1, the carbon diffusion is fast. Carbon and iron diffusion takes place. Below T1, the iron diffusion becomes more sluggish, right? And if I try to cool, and if I try to quench the steel, then you will have martensite, which is a diffusionless transformation, which will be coming after diffusional transformation. So if I try to quench it, then there is a formation of martensite, which happens through diffusionless transformation. Diffusionless transformation. There is a martensite formation. Right, there is no diffusional transformation. Now, we will discuss these transformations in next session. So at first, I have gamma plus ferrite, and if I try to cool it up to T1, and if I try to maintain here, then I will have the Bennett structure. The Bennett structure has the different morphology. You still have alpha plus Fe3C, but the morphology is different. Here you have lamellar. Here you have rods and leaves, or leaf-like morphology. So this will be discussed in next session, right? And depending upon the cooling rate, you can achieve different types of morphology of microstructure in states. So this will be discussed in next session. So yeah, that's all.